Okay, here we are with the nephron. Today's discussion is all about the loop of Henle and what's going on in the loop of Henle. There's a couple of things. Well, just as a quick reminder, when we're talking about the loop of Henle, we're talking about this region right here. And as we mentioned previously, the loop of Henle primarily to reabsorb salt. It's going to be upwards of 25% of the total salt reabsorption, and to reabsorb the last little bit of water. Remember, we were able to reabsorb water in the proximal convoluted tubule, 2/3 of it, but that was all passive, and it's the best we could do passively. Now we need to do it actively because I want more water back. So another 15% of water, and it's critical that we get that back. There's a couple of things about the loop of Henle that make it work. And as we look at it, let's just consider, here's the loop of Henle, it goes down, it's going to come up. A couple of things that I want to point out. Flow first goes down and then goes up in a countercurrent sort of way, and that's going to come into play as we talk about countercurrent multiplication in just a minute. But for right now, we need to recognize two things. The descending loop is permeable to water. This happens through aquaporin channels. This is very different than the ascending loop. The ascending loop is permeable to salt. And we can even divide the ascending loop into two parts. Okay, we've got the down here, the thin, and above this, the thick ascending loop. The thin is permeable to salt passively, so this is passive salt movement, but the thick is all about active movement of salt, and that's what we want to focus on. It's essential that we understand these differences. Coming down on the descending side, I'm only permeable to water, not salt. Going up on the other side, I'm only permeable to salt and not water. And the whole purpose, remember, is to find a system that allows me to reabsorb a lot of water so that I can recover that. How does it work and why is this important? Well, what we're going to see as we look at this, the countercurrent movement going first down and then up allows us to build a salt gradient. This is really important, as we'll see, to the point, of course, we know that the filtrate coming in is isoosmotic, which we know is 300 millimolar, but at the extreme depths of these juxtamedullary nephrons, we could approach upwards of 1200 millimolar, or even more. And so 300, 400, 500, 600, 700, 800, 1,000, 1,200. And then as we go back up, we end up coming out at about, actually it's less than 300, we come out at about 150. So we get really, really salty as we think about this gradient. It just gets very, very salty as we move down into the depths of the kidney medulla. What we want to do now is walk through the process of building that gradient, starting from scratch, a brand new kidney, never run before, and we want to show you how to build that gradient. And the process for doing that is called countercurrent multiplication. Let's take this view. This is our loop of Henle, and let's put in, we said that we were going to start from scratch. I'm going to use a couple of different colors to help us highlight the orientation. First of all, we'll start with the filtrate coming in. We'll do this in blue. We come in, like we said above, at 300. Of course, the very first time this kidney runs, everything's going to be 300. So we'll continue 300 here, 300 here. Everything is at equilibrium, so let's transition over to the interstitial space at equilibrium as well. 300, 300, 300. And of course, up the ascending loop, we can do that one in yellow at equilibrium, 300, 300, and 300. Okay, countercurrent multiplication can be broken down into just a couple of simple steps. Number one, transport of salt. And everything we know about osmosis tells us what step 2 is. Step number 2 is water moves to establish equilibrium. Let's think about this transport of salt really quick. This can actually be broken down into 2 different phases, which we mentioned earlier. In the thick ascending loop on the top, we have active transport. And this is done by a channel called an NKCC2 channel. And it really is what it says. This channel will move simultaneously 1 sodium, 1 potassium, and 2 chloride ions. And it's a symporter. It will all move in the same direction into the cell. So that's a key player in this process, is the NKCC2 channel. The passive movement that happens in the lower ascending loop is just done through simple passive salt channels. Let's see now if we can figure this out. So, first thing we're going to do, transport of salt, primarily through active transport. What we're going to see then is the movement of salt. Again, it only happens on the ascending loop. Salt is going to move from the filtrate into the interstitial space. A couple of things that we need to know about this. This transporter, we can move salt to the extreme. It can maintain a 200 milliosmolar difference. In other words, right now I'm at equilibrium, 300 and 300. If I was able to move 100 milliosmoles of salt from the filtrate into the interstitial space, that will allow me to establish this 200 milliosmol difference. And we'll see that if we write down some new numbers. So let's do the salt numbers first. That's going to go 200, 200, and 200. Because all of the salt was pumped into the interstitial space, now we have 400, 400, 400. And please again recognize the difference between these two is 200 milliosmolar. That's about the strength. I can't move any more than that. Of course, we haven't changed water yet, so the water still is at 300 all the way down. Now, step 2, we said the water moves to establish an equilibrium. What do we know about water? Water follows salt. Because there's more salt gradient in the interstitial space, water is going to follow in that direction. It will only come from this side of the filtrate, because remember, it's only on the descending loop that is permeable to water. Water can't come from anywhere else. So as this happens, it will move until we establish a new equilibrium. And so following osmosis, we have the following numbers: 400, 400, 400 in the interstitial space, 400, 400, 400, and over here 200, 200, 200. The next thing we have to recognize is that water is always flowing. And so we're going to see movement in that direction. with this rotation, remember what's always coming in. Let's start with the water side. 300 milliosmolar concentration is always coming in. So with that rotation, we now have 300, 400, 400. This bottom 400 is now over on the other side as a 400, and we have 200 on top of it and 200 on top of it. We haven't, as of yet, changed anything here. So this is still going to be 400, 400, and 400. But after movement, what do? We recognize that water will follow salt. And so there is movement of water still in this direction, so much so that the interstitial space starts to be diluted out, back to what it's seen with the water. In other words, as we seek equilibrium, again, osmosis, we're going to change these interstitial values, and they're going to look like the water values, 300, 400, 400, to match the water values, 300, 400, 400, and I haven't yet done anything with the salt, 200, 200, 400. We've essentially gone through one round of establishing this salt gradient. We're nowhere near the 12 or 1400 that we need to achieve, but I think you can appreciate we're starting to get there. The next step is repeat. So to do this, we first need to actively transport salt. The active transport of salt, again, is going to go from here to here, and I'm going to look for a difference of 200. So to do this, I know that if my difference is 200, I'm going to take 200, and then I'm going to subtract that from the difference between the concentration in the interstitium minus the concentration that I see in the ascending loop, and because I have to split that between two different compartments, I'm going to divide it by 2. So 300 minus 200 is 100. 200 minus 100 is 100 divided by 2. This equals 50, which means that I can add 50 here and subtract 50 from this side on this first row. So let's see what that gives me. That gives me 350. Let's make sure this is active transport. 350 there. 150 here. Now this next one, I'm at 400 and I'm at 200. The difference there, 400 minus 200 is 200. I've already got my maximal strength of gradient, so I can't change that. Right? This one right here won't change. But this one, there is no gradient. It's 400 in the interstitial space, 400 in the filtrate. That one I can change, and I'm going to add 100 to one side, subtract 100. So let's fill in these numbers. That's going to turn. This one stays at 400, but this one goes up to 500. This one stays at 200. This one goes down to 300. Again, recognize the difference. Right? If we're looking at the difference, we'll just show delta there. The difference between all of these is 200 milliosmolar concentration difference. That's the strength of what we can do with the transport of salt. And of course, we haven't yet moved water. This is 300, 400, 400. But that's the next step. So after we've moved the salt, we know that water is going to follow. We would expect this then to equilibrate by osmosis, and the water is going to flow toward the salt to match those numbers. So these numbers don't change. 350, 400, 500. As water flows, it will match 350, 400, 500. And the salt, of course, we were seeing 150, 200, 300. Now we've gone through this second round. What's going to happen next? That's right. We rotate. You can start to see where this is going. Let's run through one more round real quick. Do you see what it looks like as we rotate? We know that coming in new is going to be 300. Now I've got 350 beneath, 400 beneath that. The 500 has moved now over to the other side. It's in the ascending loop with 300 on top and 200 on top of that, and 150 is what left down the distal convoluted tubule. With that, we know that the interstitial space now is going to become diluted out and equilibrate as well. So this is going to continue to be 300, 350, 400 as it's washed out with water. And now we're just going to repeat the process. And we keep running this over and over and over again. And I think you can now begin to appreciate what we're seeing. The establishment through here of a salt gradient. And when we're talking about the medulla, this gradient is going to go from 300 all the way down to 1200, and then it will come all the way back up. But with this gradient, with the salt, remember, water follows salt, and so those juxtamedullary nephrons that dip deeply into this gradient, this is where I'm getting that last 15% of water that I need back. A couple of notes. As we go back up and look at our nephron, it is important to recognize that the vasa recta is actually running countercurrent to this whole thing as well. And that's an important thing. We don't want to go into the details too much, but as the salt and as the water are removed from the filtrate, it's important that they get picked up in this countercurrent exchange system to maintain the strength of the gradient. It is also relevant to note, right, if we have over here, we have our collecting duct. I have urea pumps over here. Depending on what kind of feedback the body is receiving, whether or not it wants to increase or decrease the strength of this gradient, I can open up these urea pumps, and urea can come out and contribute to, because it's a solute, urea will contribute to the strength of this gradient and help the reabsorption of water as necessary.